this live TA discussion. So today we are going to discuss about the. Today we are going to discuss about the observability and the pole placement method for to design a control law. Basically, yeah, yesterday week we have discussed about the controllability and stabilizability and all those things. And today we're going to discuss about the observability, detectability, and pole placement techniques. So let's start. Let's share my screen first. I hope you are my screen is visible to you. So yes. So the observability is basically what is that? Having the informations of the output, we basically get the information of the initial condition of a system, right? So this is basically the observability. If it is possible, then we say the system is observable. If it is not possible, then we say the system is not observable. Means we from the output, if we get the information of the system's initial condition, then we can say the system is observable. Okay. So the first technique to check the system's observability is that we have to check observability matrix like a controllability matrix. Let's say we have a system. So let's say we have a systems like this: ax plus bu and y is equal to cx plus du. So when we talked about the controllability, we are basically concerned about the system matrix, which is A. Let me just denote this is a system matrix. This is input vector for case of a single input system, or we can say input matrix if the system has multiple input. This is output vector for case of a single output system, or we can say it's a output matrix. So in general, in case of if we talked about the proper system, we have talked about the proper transfer function of proper systems, like the number of poles, number of zeros are less than the number of poles, right? So in that case, D is basically considered as a zero. So right now we have talking, we consider that D is zero. So these three are the things. Okay. So when there is a controllability, when we check the controllability of the system, we basically concern about the matrix A and B, and we generate a controllability matrix which involves the B matrix and A matrix, and we check whether that matrix is a full rank or not. And in case of observability, we check an observability matrix. Let's say we signed as a big O, and we check that C transpose A transpose C transpose A transpose square C transpose. In that way, A transpose to the power n minus 1 C transpose. The rank of this matrix, the rank of this matrix O should be m. Let's say my x, this is belongs to sign, x belongs to, or rather I would say x equals to n cross 1 vector. Let's say A equals to n cross n matrix. Okay. So the system rank should be, if the system rank is, if the rank of this matrix is n, which is this n, then we can say the system is observable, right? This is the condition. So now we will see. So how we'll see, what are the procedure to check the rank of a system? The first thing we, if the system, if the matrix, if this matrix is square matrix, if this matrix is a square matrix, then we can see that whether the system is singular or not. That means we can see that the determinant of that matrix is non-zero or not. If this only possible if the matrix is square matrix. If the matrix is not a square matrix, in that case we will, what we will do, we will do a we use a Gauss elimination method, or you can say row reduce echelon form, which is nothing but we just reduce the row and find out the linearly independent rows or linearly independent columns. So we will see in example. Yeah. So the first example. So the example is given to you. The system is x dot equals to, there is a 3 cross 3 matrix, 0, 6, minus 5, 1, 0, 2, and 3, 2, 4. Okay, and this is x plus 0, 1, 2, u, and y is equal to 1, 2, 3. Again. So this is basically a single input. This is basically a single input, single output system, right? So now we have we find out the observability matrix. So for observability matrix, we know that this is a C transpose, this is a C matrix. So C transpose would be 1, 2, 3, right? Now you have to find out the A transpose, C transpose, A transpose, C transpose, right? What are the A transpose, C transpose? Or rather, you could say either you use this form, or you can use. Let me just put another structure, or you can write O equals to, so this O equals to, in this structure, C, CA, C A square, C A to the power n minus 1. This is also the structure. You can do it in that format or as well. If you do it in that format, you also get the, and we have to find out the rank of O should be equals to it. So either you do this, but these two format are same format. Okay. So A transpose, let's say I'm doing, I'm not doing the A transpose format, I'm doing the normal AC. Okay, so sorry, C into A, C into A. That means 1, 2, 3, and it is multiplied with A, which is 0, 1, 3, 6, 0, 2, minus 5, 2, 4. And this is 2 plus 6, 2 plus 9, 11, 6 plus 6, 12, and that is minus 5, 4. That is minus 1 plus 12, that is 11. Okay. And then you have to find out the C S square. This is a 3 cross 3 matrix. So obviously up to C S square, we need up to C S square. C S square is basically, what is C S square? C S square is basically C A into A, right? So that means 11, 12, 11 multiply with 0, 6, minus 5, 1, 0, 2, 3, 2, 4. This is equals to plus 33 is 45, then 88, and then 30. Okay. So what you can do, the observability matrix O is C 1, 2, 3, and then CA. Let me write down that first. C, CA, CA square, so which is equals to 1, 2, 3, and then 11, 12, 11, and then 45, 88, 30. So as you can see, this O matrix is a square matrix. So to check the rank of this matrix, what we can do basically, we have to find out the determinant of. We can check the determinant. We can easily do the row elimination process and then check whether there exist independent rows or not. This is also a way. This checking of rank can be applicable to any matrix, whether it's a square, non-square, any matrix. But determinant, the checking determinant and then talk about the rank is only possible in case of a square matrix. Okay. So it's a determinant of O, which is 1, 2, 3, 11, 12, 11, 45, 88, 30. So it's a big determinant. So if you do this determinant, you can see that the system is non-zero. It will. I'm not going to do the determinant. It is very easy to do it by yourself. So that means since determinant is non-zero, that means the observability matrix, the observability matrix O is non-singular. Non-singular means whose determinant is not zero. If the determinant is zero, then I would say that this matrix is become singular. So this is non-singular. Therefore, the rank of O is equals to 3. So rank is 3. That means rank is n. So it's the full rank. Full rank. Therefore, system is observable. So observable, what does it mean? It means that, let's say, if we do not so let's say we can in case of this system, let's say we are basically extracting one output, okay, or a linear combination of output, but we require the system states. So from the output, if the system is observable, if the system is observable, and let's say forget about everything. Let's say that your system is a vehicle. A vehicle is your system. Okay. And in case of vehicle, what are the states? The states are position, velocity, and acceleration. Right. So let's say, but to find out the control input, which we will going to discuss later in this topic, to find out the control signal, we need the three state: position, velocity, and acceleration. But from the output from the system or the sensor that we are basically using that sensor, we are basically getting only, let's say, position and velocity. We are not getting the acceleration, or rather you can say that only we are getting the position, velocity, and acceleration we are not getting. That means, so is that mean that we cannot design the control signal? No, we can design the control signal. First we have to check the system is observable or not. If the system is observable, that means we can use or we can design a system observer, which we will discuss in the next class. What is the system observer? So we can design a system observer based on using the system of the observer. We can estimate the other state, because we already have the position, we already have the value, we already have the position states using the sensor. So we need to estimate the velocity and acceleration, these two states, using this observer. Using this observer, we will estimate the velocity and acceleration, and then we can design the controller. So basically the purpose is, if the system is not observable, it is not possible to design a classical observer for that case. Okay. If the system is not observable, it is not possible to design the classical observer for that case. But if the system is observable, we can design the observer and we can estimate the systems which are not measurable. Okay. So that's why this checking is very much required. So here system is observable. Now check the next example, example 2. The same for the observability check. The system is given. So here basically, since we are basically, let's say, what is the system is basically given. Let's say it's a -1 0 0 0 -2 0 and 0 0 -3 6 1 0 1 2 1 1. This is u, and y is equal to 1 1 2 and 3 1 5 x. So you can see this is basically multi-input, multi-output system. That means we have a 2 input. So let's say instead of using that, I am using proper structure x1 dot, x2 dot, x3 dot, and here x1, x2, x3, and this is u1, u2, and this is y1, y2, and x1, x2, x3. So we have multi-output, multi-input. That means 2 output, 2 input system. So in that case, it would be not easy to the observability matrix will never be a square matrix. It will always be a rectangular matrix. You can see that. So we have to find out the observability matrix. For that we need first C transpose. So what is the C transpose? It's 1 1 2, then 3 1 5. This is C transpose. Okay. Now you have to find out the A transpose, C transpose. What is A transpose, C transpose? So you can see that A is a diagonal matrix. So whatever the transpose we will take, it will always be a same. A transpose equals to A. And here C transpose. 1 3 1 1 2 5. Okay. So what will you get? -1 -3 -2 -2 -6 -50. This is A transpose, C transpose, and then A transpose square C transpose, which means A transpose into A transpose C transpose. So basically -1 0 0 0 -2 0 0 0 -3, and then -1 -2 -6 -15. So the answer is 1 3 4 4 18 45. So what would be the observability matrix? This is A transpose, A transpose, C transpose, and A transpose square C transpose, right? So as you can see, this is 1 3 1 1 2 5, then -1 -3 -2 -2 -6 -15. This is A transpose, C transpose, and the third one is 1 3 4 4 80 45. So this is a rectangular matrix. So here, basically here, X is 3 cross 1 vector, A is 3 cross 3 matrix, B is 3 cross 2 matrix, and C is 2 cross 3 matrix, right? So this is basically 3 cross 6 rectangular matrix. So how we will check the rank of this system? We have to do the row elimination method. Okay. So I think I don't need to write this. I mean, or rather, I would put it. Or rather, I just remove this, and this is pretty obvious to, and this is no longer needed. Okay. So row elimination method. So in row elimination method, what should we do? We have to find out, we have to make a constant this complete this term, and we will do sorry, this term we have to make constant, and we make these two terms 0, and then we check whether this term is a non-zero term or not. If this is a non-zero term, we will make this term is as a zero term, and we will check whether any independent rows exist or not. Okay. So first, what we can do, we can change row 2 by simply difference between row 1 and row 2. And what we'll get? 1 3 minus 1 minus 3 1 3. Okay, this is 0, this is minus 2, this is minus 1, this is 1, this is 3, and this is 1. Okay, another thing we can do, let's say not do anything, or let's do R3 is equal to R3 minus 2 R1. Okay, so 0, this is minus 1. Okay, R3 minus 2 R1. Then this is minus 2, this is minus 9, this is 16, this is 39. Okay, so next what we can do, so we made these two element to 0, and this is non-zero term exists, and so we have to make this term to 0. Okay, so for that what we should do, let's say we again change the R3 to, let's say 2 R3 minus R. So now we can further do the row elimination. We can further make this term to, we can further make this term to 0, anything, but at least we can see that there exist 3 non-zero rows. Whatever the row elimination process you can do, ultimately you find out that there exist a 3 non-zero rows. Since there exist a 3 non-zero rows, so there exist 3 linearly independent rows, therefore rank of observability matrix is 3, which means it's a full rank. So up to this point, I assume there is a no Up to this point, I assume that there is a no problem to, there is nothing to there is no problem to understand. Okay. So now move to the next thing, which is Gilbert test for checking observability. So this is one test to check the observability of the system. Now the Gilbert test. So Gilbert test, in the previous class we have seen that there is a Gilbert test for checking the controllability. So first of all, whatever the matrix you have given, you just find out the, you need to find out the similarity transform using that A equals to sorry, lambda equals to, or no, sorry. So A equals to P inverse lambda P, right? And B equals to P inverse, I think, just let me check. P A P inverse. P lambda P inverse. P lambda P. So the main thing is in Gilbert test for checking of observability, what you need to do, whatever the matrix is given to you, you have to find out the similarity transformation. So you have already seen how the similarity transformations is, how the similarity transformation we can do. And using the similarity transform, we have to make the system into a diagonal form, and then we check the system. We check that whether we can basically make the system, is the system observable not, or controllable or observable or not, by checking only the matrix and corresponding input vector or input matrix, or the output vector or output matrix. So we have seen in the previous lecture that the system is basically using the Gilbert test. We have seen that the system is how we'll check the controllability, right? Now we will see that how we'll check the observability. So just a minute, I'm just checking. So the similarity transform is like, this is the similarity transform. Okay, if we choose, let's say, uh, A tilde, let's say this is P inverse A P, right? Yes. B tilde is P inverse B, and C tilde is C P. Okay, so you have to find out this conversion and then we can check. So here I have a few examples which already have the conversion, and I'm just going to tell you that how we will check. So example number one, the system is, so let's say you have a systems like that, x dot equals to -1 0 0 0 -4 0 0 0 -5 x plus 0 1 1 0 1 1 u and y equals to 1 3 0 x, right? So the thing is, first of all, you have to check if the system has a distinct eigenvalue, then we will get this kind of diagonal structure. Okay. So once we get the diagonal structure, that means these three are the eigenvalues, distinct eigenvalues of the system. So we have to check the corresponding columns of the C matrix. Is the element of the corresponding column of the C matrix are 0 or not? So the corresponding column of this -1 is 1, which is non-zero. Corresponding column of -4 is 3, which is non-zero. But corresponding column of -5, which is 0. That means we can observe this state, state 1, state 2, but we cannot observe the state 3. So that means in that case, so column of C vector corresponding to distinct eigenvalue should be non-zero. Therefore, the given system is not fully state observable. Okay, so system is not fully state observable in that case, because the column corresponding to -5 is 0. Now going to the next example. Now the next example is we have a repeated eigenvalue. So we have seen that if we have a repeated eigenvalues, we will not get a complete diagonal system. We will get some sort of a Jordan block, right? So we will see that this system has a two Jordan blocks corresponding to two eigenvalues. So as you can see, here exist a two Jordan blocks. This is the first Jordan block and this one is the second Jordan block. Okay. So the first Jordan block corresponds to eigenvalues -1 and the second Jordan block corresponds to eigenvalues -2. So how you will check the controllability? You see the previous lecture or previous note. And for the case of controllability, observability, what we have to see? We have to see that in case of Jordan block, the first column correspond to the first row of the Jordan block is non-zero. That means this is the first, this is the first row of the Jordan block. Okay. So this, with respect to this term, we have to check that this is the first column. So if this column is non-zero or not, in that case, this is non-zero. Okay. In that case, this is non-zero. Okay. So that means the system is observable. So what you can say? You can say that means first column of C matrix corresponding to Jordan block shall not have all zero element. That means all elements shall not be zero. It might exist a one is zero, another should be one term is zero, another term should be one or two or non-zero any term. So the first column corresponding to every Jordan block should be non-zero. So since therefore this condition satisfied, therefore the system is observable or state observable. Okay. Now next, the last example, I will then move to the next segment. This is a 5 cross 5 matrix. So here exist three Jordan blocks, or rather you can say two Jordan block and one distinct eigenvalue. So as you can see here exists a three Jordan block, this, this, and this. Or you can say the two Jordan block and another one is distinct eigenvalue. So what we have to check? We have to check that the first column corresponds to Jordan block. This is the Jordan block and corresponding to the first column corresponding to this is non-zero. This is the Jordan block and the first column corresponding to this is non-zero. This is the Jordan block and this is the corresponding to non-zero. That means system is state observable. Okay. So this is basically the concept of Gilbert test for observability checking. The next thing is detectability. So detectability that we have already seen that in case of controllability, we have seen that there is a weaker condition which is called a stabilizability, right? That means it says that in case of stabilizability, it says that let's say our system is not fully controllable, but that means we cannot design any controller. No, that's not the thing. So the weaker notion says that if the uncontrollable modes or modes or the eigenvalues correspond to the uncontrollable states are stable and the controllable modes are unstable, then we can say the system is stabilizable. We can still stable the system. So detectability is same thing. It says that this is basically the weaker condition for observability. So it says that if unobservable modes are stable and observable modes are unstable, or rather say unstable, those modes are unstable if it is observable, and the unobservable modes are stable, then we can say the system is detectable. So basically a thing is unobservable modes are stable and unstable modes are observable. Okay, so let's see, we can see this using an example, a small example. So the system is given, it's like that: x dot equals to -1 0 0 2 x plus 1 1 u y equals to 0 1 x. So as you can see, this is this is stable mode and this is unstable mode, right? So what I have said, or what the logic said, what the logic says that if unstable mode are observable, so that means in case of our diagonal matrix, so we can see by directly that this unstable modes is observable, right? So there is a non-zero element over here. So unstable mode is observable and unobservable mode is stable. Unobservable modes are stable. So the system is therefore system is detectable. Okay. So this is basically the weaker notion of observability. Okay. So now move to the next segment, which is a pole placement. Before moving to the next segment, there is a duality principle. So let's talk about that duality, principle of duality. So this is principle of duality for controllability and observability. Okay. So the duality principle says, let's say I have a system S1 which is like that: x dot equals to ax plus bu and y is equal to cx. This is the one system, and I have another system S2 which is x bar dot is equal to a transpose x bar plus c transpose u, and this is y bar equals to b transpose x. This is a system, dual system, system 1 and system 2. So duality principle says that if if a system is completely state controllable, if the system is completely state controllable, then its dual system, or rather we can say transpose, it's better, it's not a correct word because transpose is not a, it's a dual system is always state observable, right? Or vice versa, whatever the thing is, right? So it says, so how it is possible? Let's see. There is no. It is not a proof. Uh, so for the first case, first system, let's say S1. S1 is a system. So for system S1, we know the controllability matrix. This is basically B, AB, A square B up to A to the power n minus 1 B. Okay. This is controllability matrix. And if rank of C is full rank, then system is state controllable, right? Now for case of system 2, which I have said that system 2 is the, which I have said the system 2 is the dual system of system 1. So this, for case of system 2, what is the controllability matrix? It's a C transpose, A transpose, C transpose, A transpose square, C transpose. Just a minute. What I have said, a system is complete state controllable. Its dual system is always a state observable and vice versa. Right. So here you can see system S1 is a, if the rank of system, this matrix is n, then system is a state controllable. If the system is state controllable, for case of system 2, the system is state controllable. So this would be the thing, right? The rank of this matrix should be n. For system, I think I should do it in that format. Okay. This is the one thing. And the second thing is observability is C transpose, A transpose, C transpose, A transpose square, C transpose. For system 1, this is A transpose to the power n minus 1, C transpose. This rank of O should be n. System is state observable, right? And here for case of system 2, this is the one system. This is a dual system state controllable, and the observability is B transpose of transpose, because in case of dual system, this is the B transpose, right? B transpose. So we have to take transpose of transpose. That means it should be a B. So rather, okay, let's say I'm saying it's B transpose transpose, then A transpose transpose into B transpose of transpose, then and continuing this way, A transpose of transpose whole to the power n minus 1, B transpose of transpose, right? So this is the thing. So this is become B, AB, A square B up to a to the power n minus 1b. So rank of O is n, implies that dual system is state observable. So rather I should put here this is 1 and these are A and B, A, B. This is 2 and I put this one as A, B. So what this what the theorem says? Theorem says that if a system is a completely state controllable, then its dual system is always a state observable, right? And vice versa. So system 1 is the original system. It's a state controllable. Okay. From 1A, we get that this system 1 is a state controllable. And from 2B, we see the same condition. 1A and 2B are the same condition. That means the systems, if the dual system is state observable, then the system is state controllable. Similarly, 1B and 2A are the same condition. So here, 1A and 2B are the same condition. Similarly, 1B and 2A are the same condition. So that means it is quite obvious. These two are same condition. That means one is possible when another is possible. We cannot say if the dual state observable is not, if the system is dual system is not fully state observable, and if we say the system is fully state controllable, these two are contradicting. Okay, because of this have a same condition. So this is the duality principle. So now moving to the next segment, which is the pole placement. The next segment is state feedback by pole placement method. Okay, so pole placement method, or sometimes you can see in the literature or in some books, you can see it's a eigenvalue assignment. So this basically is same thing. So basically, what is the what we are basically designing? We are designing a control law. Let's say u is equal to minus kx. So we are basically designing this u, and this kx is the k is basically the design parameter. K matrix or k vector is basically the design parameter that basically we are going to design. So we are going to design this k vector based on the requirement of the designer. Let's say I'm the designer, or I'm the one who says the designer that we need the system A, the all the eigenvalues of the system A or all the poles of the system A should lie in the particular location, in particular left half of the complex plane. So this is basically the my desired position of the pole, and this is the thing that I have said to the designer. So designer will design the K matrix or K vector based on the as a multi-input or single input system. We design this K matrix of K vector such that when this U is equal to minus Kx applies to the system will behave accordingly. The system behaves accordingly means obviously if the poles are in the desired location, systems behave according to the person's requirement. Okay, so this is basically the procedure. So we basically here, so we have a systems like that. x dot equals to ax plus bu and y is equal to cx. We are considering the proper system and we are designing. So u is equal to minus kx. Okay, when design this u is equal to minus kx. So this is basically the design parameter. Right. So there are three procedures how we can uh, design this k parameter. So we will see by using the examples. So the first example, let's say I'm choosing this example. So system matrix, I'm not going to write down the whole system, or rather, let's say I'm writing down the whole system. This x dot equals to ax, which is 0.5112x plus bu, a single input system. I'm not writing down the output equation because not required. This is a system given system. Then design a control law such that the closed loop poles are desired to be located at, say, s equals to -1 plus minus j. So basically this -1 plus minus j, these are the desired pole location. So I want my system's closed loop poles should lie in this region or in this particular this position. Okay. For that, I have to design a system control law. Okay. For that case, first I have to check where the system, this system, first I have to check where the system's eigenvalue is basically located. So poles of this means eigenvalues, right? First I have to check the where this eigenvalues basically the system A is 0.5112, and what we should do for eigenvalue, determinant of lambda or s whatever. Since I have already chosen that s term, so I'm just using s over here. This is equal to 0. So what we get s minus 0.5 minus 1 minus 1 s minus 2. So this will give you two eigenvalues, s equals to 0 and 5.2 or sorry 5 by 2 or 2.5. These are the two eigenvalues. So that means you can see our systems is basically unstable, right? If we do not without any control law, our system is unstable because eigenvalues lies in the right half of the complex plane. Okay, so we have to stabilize the system. We have to shift the system's eigenvalues from right position to the left position. So desired pole location s equals to -1 plus minus j, right? So that means What would be the desired characteristic equation? Desired characteristic equation. It would be S minus S plus 1 plus J into S plus 1 minus J, right? So let's say I am just writing down it as a P of S. Okay. This is our desired characteristic equation, right? So that means what is the characteristic equation would be? This is S square plus twice S. This J will J minus J1 and this 1. Otherwise, all this will cancel out 2. This is my desired characteristic equation. Now I want a closed loop poles should lie in this region. Okay. So I have to, this is the first procedure. There are another procedures. The first procedure is, so I have to first what, let our U is equal to this Kx. Kx. So what is K? This is basically K1 and K2 into X. Right. So what is my closed loop equation then? A is equal to Ax plus Bu. This is my system. Now I have Ax minus Bkx. That means A minus Bk into X. This is my closed loop system. Right. So what is A minus Bk? So this is A. This is B. B is 1 and 1. And this is K. K1, K2. So what I will get? 0.5112. This is K1, K2, and this is K1, K2. So this is 0.5 minus K1, 1 minus K2, 1 minus K1, 2 minus K2. And I have to find out the determinant of this closed loop system. Okay. So determinant of Si minus A minus Bk. That should be 0, right? So this is my closed loop characteristic equation. So write down it that way. Closed loop characteristic equation is determinant of Si minus A minus Bk. This is, let's say, Qs, right? What is Si? This is A0, 0S minus what is Bk? A minus Bk, it's 0.5 minus K1, 1 minus K2, 1 minus K1, and 2 minus K2. And take a determinant of that. What you will get is S minus 0.5 plus K1. This is minus 1 plus K1. This is 1 minus 1 plus K2. And this is S minus 2 plus K2. Right? Now take a determinant of that. What we will get? We will get S square, or rather I should do it accordingly. Is S minus 0.5 plus K1 into S minus 2 plus K2 minus K1 minus 1 into K2 minus 1. So it is A square minus 2s minus 0.5s is minus 2.5s plus k2 plus k1 okay a square minus 2s plus k2 0.5s plus 1 minus 0.5 k2 k1 is minus 2k1 plus k1 k2 minus k1 k2 plus k1 plus k2 minus 1. So 1 1 k cancel out, k1 k2 cancel out, so we will get a square minus 2.5s plus k1 plus k2 into s plus this is plus k2 minus k1, right? It's a so k2 is 0.5, sorry, plus 0.5 k2 minus k1. So this will become a square minus 2.5 minus k1 minus k2, or rather s plus 0.5 k2 minus k1. So this is my system, right? Now let's say this is my characteristic equation. Now this is the desired characteristic equation. I am just doing this equation as number 1 and doing and marking this equation number 2. Okay. Now equating equation 1 or comparing equation 1 with equation 2. So what we get, it's a s square plus twice s plus 2 is equals to s square plus 2.5 plus k1 plus k2 s plus 0.5 k2 minus k1. So what we'll get, we get k1 plus k2 minus 2.5 equals to 2 and minus k1 plus 0.5 k2 equals to 2. So from here we'll get k1 plus k2 equals to 4.5, and this is minus k1 plus 0.5 k2 equals to 2. So this, by cancelling out, so what we'll get is a 1.5 k2, we get 1.5 k2 is equals to 6.5, or k2 equals to 6.5 divided by 1.5. It's 13.13 by 3. And what is the K1? K1 equals to, put the value of K2 over here, 4.5 minus 13 by 3, and you will get 1 by 6. So what is the K matrix? That K matrix that you get, K1, K2 is 1 by 6, 13 by 3. So this is your answer. Okay. So that means this is the control design. This is the feedback matrix or feedback vector that you have to be, you basically design based on the desired requirement. Now there are another procedure by which we design this same thing, by which we design the same, we design the K matrix. Okay. So let's say I have taken another example, another small example. I'm going to take it. I mean, small example in the sense like the matrix is a, okay. So the next method is similarity transformation method. Okay. So similarity transfer system is, so in similarity transformation method, and then we will see the Ackermann's method, and then we will wrap it out. Okay. So system is x dot equals to 1 1 1 2 x plus 1 0 u. So find the control parameter for the above system. The desired poles are to be located at s equals to -5 and s equals to -6. So this is the example that you have given. Now you are doing it in using a defined approach, because sometimes in the questions may ask that you have to design control parameters. If there is no approach mentioned, like whether you use a simulate transformation method or the Ackermann's formula, you just say that find the control parameters where and the system desired pole to be located in this location. You can use any of this method, but sometimes if the method is clearly mentioned over here, so you have to choose this particular method, right? So for that case, what you should do? So similarity transfer method, what the similarity transfer method says. So let's say I have a system, I'm taking a z another state, which is basically in this structure, z equals to px. So p is basically a similarity transformation matrix. Okay. Similarly, we have seen in case of how we do the similarity transformation. The same. This is basically similarity transformation matrix, right? So, taking the derivative, with respect to time, what we'll get, this is x dot. So this is p into ax plus bu. Okay, this is the u that I have to choose. So let what u I have chosen, let u equals to minus kx. Okay, so put that over here. So z dot equals to ax minus bkx. So this is become p into a minus bk into x, right? Now make it into a z format. So that means z dot equals to p a minus bk p inverse into x. So this is p a p inverse x minus p b k p inverse x. So this is z dot equals to, let's say, ac to x minus bc b suffix c into k suffix c into x. Okay, so this is basically your ac minus b suffix c k suffix c into x. So this is your system. So you are basically finding out the kc, and from kc you have to find out the k. So ac is equals to p a p inverse, right? B suffix c is basically pb, and k suffix c is basically k into p inverse, right? So we have also, first of all, how to find out the p matrix. So for that case, in case of this procedure, you have to make sure that your system is fully controllable. Means, and this is only main. You can see this is majorly possible if your system is a single input system. In that case, your controllability matrix will become a square matrix, and then you can take the inverse of this matrix, because for that case we need to take the inverse of the matrix. Other than that, it is not possible to find out this. Okay, so first I have to check the controllability matrix. So since I have a 2 cross 2 matrix, so it is not difficult to find out the controllability matrix, right? So the controllability matrix, let's say C is equal to B and AB, right? So first check what is A into B. It's 1 1 1 2 and 1 0. So this is 1, this is 1. Yeah. So C is 1 0 1 1. So easily we can find, I mean, by seeing this matrix, we can say, because these two vectors are linearly independent, so we can say that this is invertible. So we have to find out the C inverse. What is C inverse? C inverse is 1 by determinant of C into adjoint of C. So determinant of C is basically 1, and adjoint of C is, this is adjoint of C. So what you will get? You will get 1 minus 1 0 1. Okay. So this is C inverse. So how to find out the P matrix? So P matrix is basically, let's say, in this format: P P A in this P a to the power n minus 1. So now what is P? P is the last row of matrix C inverse. So last row of the matrix C inverse is this. So this is I'm calling as a P, and I have to find out this up to that. And since I have we have basically a 2 cross 2 system, second order system. So we will stop up to this point. So our P matrix will become P and PA. So P is for our case is 0 and 1, and PA will be 0, 1 multiplied with A. So I will get only the last row, I will get 1, 2, right? So the system is 0, 1, 1, 2. I mean, P matrix is 0, 1, 1, 2. Again, I have to find out the inverse of this matrix. So determinant of this P matrix is -1, and the inverse is 2, -1, -1, 0. A determinant, its adjoint is this. What is the P inverse? It's the -2, 1, 1, 0. Right. So this is the transformation matrix that we get. So now we have to find out the AC. AC is, what is AC? AC is PA inverse. PA P inverse. So what is P? P is 0, 1, 1, 2. A is 1, 1, 1, 2. And P inverse is -2, 1, 1, 0. This is 1, this is 2, this is 3, and this is 5. Okay, -2 plus 2, 0, 1, -6 plus 5, -1, and 3. So this is your AC. Okay. Now what is B suffix C? B suffix C is P into B. P into B. So what is P? Is 0, 1, 1, 2, and B is 1, 0. So you will get a 0 and 1. This is B. And let's say KC equals to small kc1 and small kc2. Right? So AC minus B suffix C into KC is basically 0, 1, -1, 3, minus 0, 1, KC1, KC2. 0, 1, -1, 3. This is 0, 0. This is KC1, KC2. So what we'll get? 0, 1, -1 minus KC1, and 3 minus KC2. So we have to find out the determinant of SI minus AC minus BC KC. That is S -1, 1 plus KC1, and S -3 plus KC2. Right? So what is the value? What would be the value? It's S into S -3 plus KC2, and this is 1 plus KC1, right? So what we will get, it's the S square minus 3 plus KC2, it would be S plus 1 plus KC1. So we can write it in that format. Okay, and now, sorry. So now we have our desired location, desired pole location. This is, let's say, this is equation number 1. Desired poles S equals to -5 and S equals to -6. Okay, these two are desired poles. Therefore, desired characteristic equation, this is, let's say, this is QS, and the desired characteristic equation PS is S plus 5 and S plus 6, which is S square plus 11S plus 30. Now equate this equation 1 and equation 2. So PS equal to QS. So what we get, S square plus 11S plus 30 equals to S square plus KC2 minus 3S plus KC1 plus 1. So what we get, KC2 equals to 11 plus 3, which is 14, and KC1 equals to 30 minus 1, this is 29. So that means your KC is basically 14 and 29. Sorry. This is 29 and 14. Okay. Now your K would be Kc into P inverse, right? This is the thing, Kc into Kc, your Kc is K into P inverse, right? So if K into P inverse, sorry, this is the wrong thing. So your Kc is K into P inverse. This means that K equals to Kc into P, right? So Kc is 29 and 40. And what is P? P is uh, 0, 1, 1, 2, right? 0, 1, 1, 2. So it's a 14 and it's a 29 plus 14 is 29 plus 28. Sorry, 29 plus 14 is not 29 plus 14. It's the 29 plus 28. It's a 57. So the so basically this is your answer. So you should not stop at that point. Okay, you should not stop at that point, because this you have find out the control parameter for the similarity matrices or similar system. Okay, so you have to find out the control parameter for the new system. I mean for the original system. This is basically the similar system. This is the control parameter for the similar system. So you should not stop over here. After finding out this Kc, you have to find out K, because this is the original control parameter. So why it is required? Sometimes it is very easy to work with the similarity matrix, because in case of similarity matrix, this is 2 cross 2 matrix. That's why it is it is not very much difficult to find out the determinant and all those things. But sometimes if your system is more than 3 cross 3, okay, so in that case it would be difficult for the it would be difficult to find out this si minus a minus bk term, determinant term, because your system is too high. But once you transform it into a similarity transformation part, your A matrix is almost kind of a diagonal in structure or in controllable canonical structure. So it will be easier to find out this determinant. Whether the system is very big or small, that doesn't matter, because in that case, if your system is controllable canonical parameter in controllable canonical term, so it is very easy to this is basically, you can see, this is controllable canonical term. So as you can see, this term, you can directly put this term as a uh, in this equation, because we have seen already in the first lecture how the controllable, how can we find out the characteristic equation from controllable canonical format. Okay, so it is very easy to find out the characteristic equation, and all other calculation is very much easier to I mean, computationally, it is very efficient one. That's why we will do it. If your system matrix is very small, it is not, this procedure is not required basically. But for a higher dimension system, this is required. So this is your final answer. Okay. Now we will see the Ackermann's formula. Sorry. So after this, this is the last part that I'm going to talk about today. And since you have, I mean, none of you have joined over here. So if you have any queries, then please put it in a forum so that we can discuss over there. So one thing you can, one thing I just want to tell you that whichever formula you choose, whichever method you choose, the value of k will be the same, right? It is not that for the same problem, if this is the, if you try to solve this problem using, if you try to solve this problem using using the previous method that I have discussed, that only comparison is over there, you will get the same k. Or you, if you solve this problem using Ackermann's formula, you will get the same result. There is a no difference in the results. Okay, so all this formula basically generated just to easy your calculation procedure. So for Ackermann's formula, I'm going to use the different system. I'm not going to use the same key system because we know that we will get the same result. Okay. So the example is, so let's say I'm going to take okay. So I'm going to take over here 2 cross 2 system again. You can expand it to n cross n system as well. So the system is x dot equals to ax plus bu, or rather I just put the value of a over here. It's minus 15 8 15 minus 15 7 x plus bu find the state feedback controller to place the closed loop pole at minus 10 plus minus j. Okay, so this is our desired pole location. So Ackermann's formula, what Ackermann's formula says, this is Ackermann's formula also the simulator. I mean, this is basically the same version of similarity transformation problem. So here we find out the Kc. Okay, so that Kc is basically is equals to, in Ackermann's formula, this Kc is basically just a minute, or rather this K, not KC. It's better to put it as a K. So this K is basically is equal to E transpose, both are equal. It's E transpose C inverse alpha D of A. This is basically the formula. So this is basically the formula. So here, what is E transpose, or rather, what is E? E is basically 0, all 0, only the last term is 1. This is basically E. C, you all know that controllability matrix. And alpha D, what is alpha D? Alpha D of A. This is basically using the, I mean, we have seen in Cayley-Hamilton theorem that a system basically satisfy a system with a square matrix. I mean, a system basically satisfy its characteristic equation, right? So that is basically the thing is, let's say, A to the power n plus alpha n minus 1 a to the power n minus 1 plus alpha a plus a alpha naught I. Uh, alpha 1 a alpha naught I, right? So this is alpha D. So using this formula, we will find out the A of, I mean, the design parameter of the system. So all these formulas are applicable for pole placement scenario. I mean, we have already given the desired pole location, that our closed loop systems should reach to this point, or should reach to, not should reach to this point. Our closed loop systems should act like the desired characteristics. So if the pole moves to the left hand side, because the left hand side of the complex plane is basically the stable one, so we always want that our system poles should lie on the left half of the complex plane. Even since here we are not basically concerned about the zero of the system, but zeros of the system also have a significant importance for the stability, for the control purpose. Okay, but here we are not going to discuss about the zeros of the system. We are basically concerned about the poles of the system. So we want that all the poles of the system should lie in the left half of the complex plane. Even it is also required that our system, it is not possible because uh, so using the control method, using our control method, this pole placement method, we can only shift the system poles. We can only shift the system eigenvalues. It is not possible to shift the system zeros. Okay. So we are here all assuming that our system zeros lies in the left half of the complex plane. We're assuming there is a no movement, no shifting of zeros required. So that's why you can see that the characteristic equations is basically the closed loop system poles we are talking about. So system zeros is not concerning about it. I'm not concerning on this methods basically. Okay. So in our case, what is A? A is minus 15.87. This is our A. So and B is 1, 1. We have to find out the controllability matrix, and for that case, we have to find out AB, which is minus 15 plus 8 is minus 7 minus 8, right? So it's basically the controllability matrix C is B and AB. So it's 1 1 minus 7 minus 8. So C inverse is determinant of C, which is minus 8 plus is minus 1, and adjoint is minus 8 7 minus 1 1. So this is basically 8 minus 7 1 minus 1. This is C inverse, and we have alpha D. So our desired, so here desired pole location is S equals to minus 10 plus J and minus 10 minus J, right? So this is I'm extremely sorry. This is not the thing. This is basically alpha D is basically desired characteristic equation. Desired characteristic equation with A matrix. So my desired characteristic equation PS equals to S plus 10 plus J into S plus 10 minus J. So this is basically A square plus 20 S plus 101. Okay, this is 101. Now, or this is basically, or rather, I'd say this is alpha ds. So alpha dA equals to A square plus 20A plus 101 I, right? So for that case, I have to find out the A square, not very much difficult. So A square is equals to minus 15 7 minus 15 8 minus 15 7 into minus 15 8 minus 15 7, and what I will get? I will get this 105 minus 64 120 minus 71. So this is A square that I'll get. So alpha D is basically 20 into A. So 20 into A, what is 20? It's a minus 300. It is 160. It is 140. This is 101 0 0 101. What is the answer? Answer is minus 94 minus 180 minus 8 plus 96 170. This is alpha D of A. So now what is the formula of K? K is minus E transpose C inverse alpha D into A. So what is E transpose? E, as I have said, sorry, this is my mistake. This should be a vector, a column vector. This should be a transpose. That means I have a column vector. When take the E transpose, I will get E, not minus. So my E transpose would be 0 and 1. C inverse. What is C inverse? 8 minus 7, 1 minus 1. And this is minus 94, 96, 180, 170. And what I'll get? I get 86, 7 minus 74. So this is the value of K that is basically required to find out the required for the closed loop system supposed to be at this location. So this is basically the Ackermann's formula. So all these formula are basically equivalent. You can use any of the formula if there is no particular mention of the formula uses. So if there is a mention that you should use using the simulated transform, so if that is requirement, then you have to do it in this method. I just put it in a red so that it is visible. So, and if you basically ask to find out the value of the K using this Ackermann's formula, so you have to do it in this formula. Otherwise, if it is not mentioned, you can choose any of those, whichever you find it easier to solve. Okay. So this is for the today's class. So today we have studied about the observability. Previous week we have studied about the controllability. So today we have studied about the observability, how observability affect the systems. I mean, how can we get the information of the initial condition based on the output of the system? That is basically observability. And how to check this observability? We have seen the Kalman method. We have seen the Gilbert's test, and there's we have studied the weaker notion of observability, which is called the detectability. We also have studied the row elimination method, which is we also have studied it previously as well. So there is nothing to mention new. So detectability, and then we have studied the duality principle of duality for controllability and observability. Like if a system is state observable, then its dual system is state controllable. We have seen the proof, like both the condition are same. So if one is happen, other is automatically happen. Then we have seen the state feedback control policy using pole placement method. We have seen a different pole placement method. Okay. The first one is simple. It's very basically compare the desired characteristic equation with the closed loop characteristic equation using the original system state, and we find out the system poles. The next one is using the simulated transformation method. Here we just transform the system from its original position to the either diagonal, or here basically we have transform it into a controllable canonical form so that our computation is very much easier. And then we do all those things. We find out the KC, which is the control parameter for the similar system, and from KC we find out the K. From KC we find out the K matrix. This, right? And then lastly, we have studied the Ackermann's formula. So in this formula, we do not need to we do not basically need to do the simulatory transformation. we basically use this technique, use this law, and we automatically find out the system star matrix. So this is all about today's class. If you have any query, you can put it in a discussion forum. We'll discuss it over there. Okay. So thank you. Thank you for today.